Welcome to Devotional Algebra 2. Today's lesson will be on quadratic regression. All right, what we've got here is a scatter plot that shows the path of a basketball shot from the free throw line, a foul shot. And so what we have, the x represents the horizontal distance that the ball has traveled from the free throw line towards the rim, and y represents the height of the ball above the ground. So, the first point here, 0, 4.2. The 0 means that it's still at the free throw line. It hasn't moved forward at all. And it's beginning 4.2 feet above the ground because the player is holding the ball at about chest level. This point means that after it's moved 2 feet towards 2 feet horizontally towards the rim, it's now 8 feet above the ground. And then after it's moved 6 feet through the air toward the rim, now it's 12.6 feet above the ground, and so on. So first question, is there a correlation between these two things? Is there a relationship, mathematical relationship, between the distance the ball has traveled toward the rim and the ball's height above the ground? The answer is yes. It appears that there is a relationship here. These points they don't appear random. It's not just a random scatter plot, but there appears to be a positive correlation, right? It seems to be moving up and to the right. So let's see if we can find the linear regression, a line of best fit to model these points. Again, all we do is we click this little icon over here, add regression, and there's your linear regression, your line of best fit. This equation is the function that models this data with a line. You can see the r-squared value is actually very good, 0.86. That's a very strong correlation between the points. So let's use this model. I'm just going to copy it real quick here. Let's use this equation, this function, to predict how high the ball would be above the ground after it's traveled 15 feet. So the two ways that we learned that we could do this are, one, you can just use your graph. You can, 15 feet through the air, that's the x value. So just follow the line until the x value is 15 and see what the y value would be. It would be about 18.1 feet above the ground. Okay? The other way you could do it is you can replace the x value in the function with 15. And the function will follow the rule, and it will give you the value of 18.1. Same answer, right? Now, here's the thing. Is that a good model actually for this data? I know it's got a good r-squared value, right? I know if you just look at these points here, the line actually is very close to all the points. So that's why we're getting a good r-squared value. But let's pull back and use a little bit of common sense. What do we know about basketballs? They don't just keep going up like this. They don't just follow a line, right? And so if this is actually true that the ball is going to end up being 18.1 feet above the ground when it gets to the rim, it's going to go over the backboard, right? It's not even going to be anywhere near the rim. Clearly, you can see these points are not just moving up in a line, but they're beginning to do what right here? We know basketballs follow the path caused by gravity. They go up and then they come back down. So if we keep following this line, we're going to get a terrible prediction for the future of what's going to eventually happen, right? So what we need is a different kind of function, a different function to model this situation. A line is not going to do the job. So what we're going to use is called a quadratic function. If you remember from Algebra 1, a quadratic function is the kind of function that models gravity. Let's click this little drop-down menu here and switch from linear to quadratic. And you'll see that the quadratic equation comes up. The name for this kind of U-shaped arc, it's called a parabola. And a quadratic function, for those of you who don't remember from Algebra 1, it's a function that has an x squared in it. And like I said, this is the type of function that's used to model gravity. We're going to have a whole unit on this later on, so we're just going to kind of get our feet wet a little bit right now. But you can see that this is a much, much better fit for the data. This follows what the points are actually doing. The r-squared value is extremely, extremely good, 0.9999. It's an almost perfect match for the points. And now we can use this model. Since this model is so much better for the data, we can use it to make a much more accurate prediction. We can figure out exactly, or almost exactly, how high the ball is going to be above the ground when it gets to the rim, 15 feet. So if we just follow this curve to 15 feet. We get about 9.44 feet above the ground. And those of you who know a basketball rim is 10 feet above the ground, so that's probably going to be just a bit short. It's going to maybe hit the front of the rim. The other way we could do it is we could take this function, I'm going to get rid of my linear one, and just replace the x values with 15. Plug 15 into the function. And the predicted height above the ground is going to be 9.44 feet. All right, let's do a couple more examples. Here we've got an example where we're looking at the population growth in a particular place since 1970. The first thing we're going to do is we're going to label the axes. I'll show you how to do that on Desmos. All you got to do is click the little wrench button right here. And then where it says label, we're going to label the X. This is the X-axis label. We're going to label that years since 1970. And then the Y-axis is going to be population in thousands. That way, once we get going, we'll be able to remind ourselves of what the variables really mean. Next, create the scatter plot and adjust the window. Well, you'll notice that this time we don't have any actual scatter plot here. We have this image of a table, but we don't have an actual table in the calculator that it can use to make the scatter plot. So there's two very easy ways to make a table in Desmos. The first option is you could click this little plus button right here and then click table. The other way you can get the table is you could just type the word table right here, T-A-B-L-E, and it pops up. Either way is fine. I'm just going to quickly make my table. Make sure when you do this you don't put commas. If I put the comma in here, you'll see I'll get an error message. Desmos is not a fan of that comma there, so leave the commas out. Once I'm done with that, you'll notice anytime in Desmos that you make a table, it's going to give you this little magnifying glass down here. This is a really cool feature that will allow you to automatically zoom in on the data that you just put into this table. So I'm going to press the magnifying glass, and it's going to automatically zoom in on those data values. So now I can see my scatter plot. There's clearly a correlation. It's not random. It's a positive correlation. It's moving up. What do you think? What would be a good function to use to model this data? Would a linear function be a good model? Or would it be better to use a quadratic function? Well, it seems to me that it's kind of curving a bit here. Let's try linear and see how that looks. And maybe see if we can do better. If I click add regression, it'll automatically make a linear function. And that's actually an excellent fit. The R-squared value is 0.95 if you round, right? So that's very, very good. But if you switch to quadratic, that's even better. It's almost perfect, 0.9988. So this population is growing basically quadratically, right? All right, the last thing we're going to do on this screen is it says predict the population in 2030. So remember, the X represents years since 1970. We want to know the population in 2030. So the question is, how many years since 1970 will the year 2030 be? And the answer is that's 60 years later, right? 60 years. So what we got to do is figure out when x is 60, what's the value of the function? So just go out to one option is you can just use your graph, right? When the x value is 60, the function gives us a value of 5,637, right? And remember, that's actually in thousands of people, right? So it's not 5,600 people, it's 5,000 people, or 5 million, right? So 5.6 million people would be the predicted population. The other way you could do it is you could take this equation, take this function, and plug the number 60 into your function. Replace each x value with 60 so that the function can follow its rule and spit out the output of 5,637,000, or 5.6 million. let's do one more example. Here we've got a relationship between the speed that your car is driving and the gas mileage. So let's quickly make labels for our axes. Speed is x, the speed that you're driving, and the gas mileage is y. I'm going to make my table. This goes down to 75. Once you make your table, hit the little magnifying glass so you can see the data values. And clearly there's a correlation, but what kind of correlation is it? Would this be a linear function or a quadratic function? This is definitely a quadratic function, right? You can see it's got the U shape, the parabola, right? And that's because, those of you who know about gas mileage for cars, there's kind of an optimal gas mileage, right? Like, cars don't get very good gas mileage when you're driving super slow or when you're driving super fast. They kind of, once you get close to highway speeds, that's the ideal, the optimal gas mileage, or the optimal speed to get the best gas mileage. And it kind of works its way up gradually to that point and then works its way back down as you go too fast, right? So let's make a quadratic equation, a quadratic regression for this. Click Add Regression. Switch to quadratic regression. The R-squared value is very good. It's 0.97. We want to use this to predict the gas mileage if the car travels at 90 miles per hour. So two ways you could do it. You could follow the curve to 90. And the predicted gas mileage would be 14.2 miles per gallon. The other way you could do it is you could copy your equation over, replace each x value with the speed, because x is the speed that you're driving, and y is going to be the predicted gas mileage. So plug 90 into the function. It's going to spit out for you the predicted gas mileage of 14.2 miles per gallon. So don't drive your car 90 miles an hour. Not only is it super unsafe, but you're going to waste gas as well.